Okay, what I'm going to try to do as quickly as I can is a video summary of Chapter 7. Chapter 7 is relatively difficult for most people, so I hope that as many of you as possible will watch this video. So the first section of Chapter 7, and P.S., this is the second chapter that deals with inferential statistics, which is statistics that use data to come to some sort of conclusion. And here we're going to be trying to make a decision about the veracity of some sort of claim. So in all cases, we're dealing with some claim statement, and we're trying to determine whether or not to reject a null hypothesis or fail to reject a null hypothesis. So we need to move from the claim statement to this thing called the null and the alternative hypotheses. So the very first part of Chapter 7 explains the process for doing this. So here are the basic steps for writing the null and the alternative hypotheses. And P.S., the null hypothesis is typically symbolized with H and a sub-0, and the alternative hypothesis for this textbook is H with a sub-A. Okay? It can be other things. I prefer actually a 1, but you know, this is fine. I'll try to stay consistent with it. And so it says first that you write the claim symbolically. And when we say symbolically, we really mean mathematically or without words. Then you have to write what would have to be true if that claim were actually not true. And again, you write it symbolically. Then the null hypothesis is whichever of these two statements contains the condition of equality, and the alternative is the other one. Okay, so let's just do a couple of examples, and I'm looking on page 350 in the textbook. So it says a school publicizes or claims that the proportion of its students who are involved in at least one extracurricular activity is 61%. Okay, so 61% is a percentage. That means I'm doing a proportion problem. Okay, so percentage and proportion, same thing. So my symbol is going to be lowercase p, and the claim is that the percentage or proportion is 61%. The word is indicates an equal sign, and 61%, typically we wouldn't write it with the percent sign, we'd change it into a decimal number. So it'd be something like that. Okay, and notice it doesn't get the complete context of the claim, but symbolically it captures what the claim actually was, that some percentage or proportion was equal to 61%. Okay, so then in the second step we have to write what would have to be true if that claim statement was not true. So it seems logical to understand that if the proportion is not 61%, then we would write it like this. And essentially, we're just using a symbol that means is not equal to. So if you looked at this on a number line, the first one is literally just the point at 0.61. The second one includes everything to the right or to the left, you know, because all of those numbers are not equal to 0.61. And notice that it's important to grasp that taken together, these two statements cover the entire number line, all the possible numbers, and that must be true in all cases. So going on to step 3, the null hypothesis is the one that included equality. Well, that's clearly the first one. So the null hypothesis is P equals 0.16. That leaves the alternative hypothesis to be P is not equal to 0.16. Okay, so let's do the second one. It says a car dealership announces that the mean time for an oil change is less than 15 minutes. Okay, now it mentions the word mean time, so now I know that my test is about a mean. The symbol for mean is the population symbol mu, and it says that that mean time is less than, so that's the less than symbol, 15 minutes. Okay, now on a number line that would look like this. So here's the number 15, and values that are less than 15, it's everything to the left of that number, but not including that number, which is why I've left an open circle here. Now, if this statement is not true, then the mean time must be either greater than or equal to 15. And in essence, what you're doing is you're filling in all the rest of the number line. So it would be this point plus everything to the right. Okay, so in this case, the equality is here in this second statement. So for that claim statement, the null hypothesis is that the mean is greater than or equal to 15. That leaves the first statement to be mean less than 15. Now, I can't overemphasize that you have to get this right, okay, for lots of different reasons, but you're going to mostly be using technology to get to the answer. But if you have miswritten the null and alternative hypotheses, you will get other stuff down the road wrong, because you're going to have to make choices in the technology that reflect the alternative hypothesis. Another thing to know is that you need to be able to identify whether the claim became the null hypothesis or whether it became the alternative hypothesis. So notice that in this first case, the claim became the null hypothesis, right? And in the second case, the claim became the alternative hypothesis. So making the assumption that the claim always shows up in the null is not true. And you need to learn this, little stepwise procedure so that you always get the null and the alternative hypothesis written correctly. If you don't do that, you will in fact make mistakes down the road. Okay. So that's the first thing to be able to do, to take a claim written as an English sentence, make it into symbols, find the exact opposite of it, and then identify which one is the null and which one is the alternative hypothesis. Having done that, we get to, well, okay, I think I want to emphasize this here. We get to choose a significance level. It's a measure of how important the test has to be, how important it is for you to get the results right. Because essentially what it does is set the level of extremity. Okay? We call this significance level alpha. And the most common ones are 0.05 and 0.01. 0.05 is by far the most common. And so what you should see is that it sets when something is really extreme. So remember, previously in the class we've said that something is a rare event or unusual when its probability falls below 5%. Okay? So that's what we're saying here if the alpha level is set to 0.05. When it's set to 0.01, we're saying that unusual territory doesn't begin until you get to 1%. This is the kind of alpha level that we would use if we're taking data to court, okay? So it sets an even more stringent requirement on the idea of a rare event or a very unusual event. Okay, so we choose the significance level. Then, when we look at an alternative hypothesis, it defines the type of test that we're going to be running. Not the title of the test, whether it's proportion or means. That is dependent upon the claim statement and whether it's dealing with the parameter of a proportion or the parameter of a mean value. The type of test that we run is based upon the direction of whatever mathematical symbol is inside the alternative hypothesis. So here's the basis of it. If the alternative hypothesis contains a greater than symbol, then that's a right-tailed test. And you notice that if it's pointing to the right, it's a right-tailed test. If it contains a less than symbol, that points to the left, and it's a left-tailed test. And when it has the not equal to symbol, then it's a two-tailed test. And the reason that's true is because we're testing for extreme values on the right for this alternative or extreme values on the left. But if it's not equal, then I need extreme values on both the left and the right. And there are pictures inside your textbook that show you this as a visualization on a bell-shaped curve. And I'll probably draw some of those in a few minutes too. But you should never think that these summaries take the place of your reading the textbook. You really, really, especially for this chapter, need to read the text. Okay, so the next thing is to consider what distribution we need. So for proportions and means tests, which are the only two tests that we're going to learn to run in this intro class, we use the same distributions that we did in the previous chapter. So proportions tests use Z distributions, which means in StatCrunch you'll be looking for under stats the thing that says proportion stats. And means tests will use a T distribution. And again, in StatCrunch, that means that under the stat key, you're going to go to T stats. Now, just like last time, there is a rare case in which a means test could be done with a Z distribution. But in that case, you would have to know the standard deviation of the underlying population, which is a very uncommon event. Therefore, we're going to just assume that all we have to go for is the sample data and its standard deviation. And in that case, we need to use a T distribution. So that's what we're going to be doing in this chapter. Okay. So once we have written the null and alternative hypothesis, and we know what type of test it is, and we have chosen a significance level and know which of the distributions we're going to use, we can calculate a test statistic. Now, what the test statistic is a number which shows how far from the center of a bell-shaped distribution the actual data lies. Okay? So, what each of the formulas for the test statistics do is make a comparison between the samples, either proportion in this case or mean in this case, and the value of the parameter in the null hypothesis. So for proportions, I mean, a comparison is frequently in mathematics. A comparison is done with subtraction. So here for a proportions test, the test statistic is a Z test statistic, and the numerator is the value of p hat, the proportion in the sample, minus the value of p in the null hypothesis, divided by the square root of p times q divided by n. Now, you may, in isolated cases, be asked to calculate these test statistics. In the work of actually doing the hypothesis test, using StatCrunch or using your calculator, this value will be computed for you. But I'm going to do an example where I compute it, by hand. For a means hypothesis test, it's a T test statistic. But it's similar, really, because in the numerator, again, you're making a comparison between the sample's mean and the mean value mentioned in the null hypothesis. The comparison is a subtraction. And then you're dividing by s divided by the square root of n, which is essentially a version of standard deviation. And I would tell you as a statistics professor, both of these two things really amount to calculating a z-score. And remember that z-scores show you how far from the center of a bell-shaped distribution something lies. And it shouldn't be surprising to you that when the difference between the parameter in the null hypothesis and the same estimator for the parameter in the sample are far apart, it results in large test statistics. And large test statistics will be further to the extremes of a bell-shaped curve. Whether they're positive or negative, they're further away from the center of a bell-shaped curve, which makes them more likely to result in rejecting the null hypothesis. So there are actually two ways to do a hypothesis test. And the traditional way literally uses the significance level and the value of the test statistic to determine whether the test statistic falls into a range that is barred off by the critical value which represent the significance level. Now, I know that's so much hogwash to you right now, but let's say that I was running a proportions test and I had a significance level. Okay, so again, I'm going to be doing a proportions test. And I'm going to choose an alpha level of 0.05. Okay? Now, let's further say that it's a right-tailed test. That would indicate that there was some value up here on the right that was the barrier, and we call it a critical value. It's a barrier number that defines extremity. And the size of this area is alpha. Now, I can determine what that value is by using the Z table, which I'm currently looking for. Because if I look on the Z table, and I'm looking for, so this is 0.05. That means that the area here to the left is 0.95. On the Z table, 0.9500 is halfway between these two values. Okay, so that's 1.645. Now, if I calculated then a Z test statistic of 2.302, say, that test statistic would be to the right of the critical value. It would be inside this extreme region to the right. And that would cause us to reject the null hypothesis. So in the traditional method, we reject the null hypothesis whenever the test statistic falls into a critical region, full stop, whether it's to the right or the left or one of the two, left and right, for a two-tailed test. Now, turns out that there is a simpler way of making the decision that is based upon what we call a p-value. And we will use p-value here because that's what is the easiest thing to do when you are using technology. So it's still based upon this idea, but it basically tells the probability associated with the sample. Now, in this example that I gave right here, it would be, the p-value would be everything to the right of the test statistic. the area, the size of the area to the right of the test statistic. So you can see in this picture that this area associated to the right of the test statistic is smaller than the alpha value, which was the whole area to the right of the critical value. And that is the basis of decision making in the p-value system. So your technology is going to give you this thing called a p-value. It's the probability associated with the sample data, and you're going to use it to decide whether to reject or fail to reject the null hypothesis. And incidentally, those are the only two decisions you can make. You will either reject the null or you'll fail to reject it. And failing to reject the null hypothesis is not the same as proving that the null hypothesis is true. Okay? So let me give you a tiny little example of that. The same kind of scheme is used in court. So the null hypothesis is innocence. Okay? When a jury decides that you're guilty, what they're doing is rejecting the null hypothesis of innocence. But no jury ever comes back with the verdict of they're innocent. They come back with either guilty or not guilty. And not guilty doesn't mean that the person didn't commit the crime. It means that there wasn't enough evidence to convict them of the crime. And that is the same position as failing to reject the null hypothesis. Now, that may seem like a small thing, but when you make statements of conclusion, then you can never say that you prove the null hypothesis to be true. Okay, so that decision here is fairly simple. The technology is going to give you this thing called a p-value. You compare the p-value to your significance level. If the p-value is less than or equal to your significance level, then you reject the null hypothesis. Because when the p-value is less than the significance level, it is in an extreme region. When the p-value is greater than the alpha, then you fail to reject the null hypothesis. Now, you'll have to memorize this little thing here, but that's not very difficult to do. So once you make your decision, and I'm going through all this quickly, but then we're going to do some problems, okay? So once you make your decision, then you have to write it out. You have to return it to English words. And so here's what you do. You determine if the null hypothesis came from the claim or didn't. And then you determine whether or not you rejected the null or you failed to reject the null. And then you use this table, which I took directly from page 356 in your text. And you're not going to have to memorize this on your test. I will send them a copy of this. But you do have to know how to use it. So if you rejected the null hypothesis and the claim became the null hypothesis, then what you do is say there's enough evidence to reject the claim that, and notice it's ... because you have to restate what the claim was there. Now, I know we're all kind of lazy. I am too. But the truth is that if you simply stop and say there's enough evidence to reject the claim, or you just say reject the claim, then I'm going to count that wrong. Because you have to bring this back full circle to what the claim actually was. And you always know what the claim is because the claim was stated to you in English words at the beginning of the process. Okay, so that probably seems like a lot, and it is, sort of. So I'm going to do two different kinds of problems because I want to keep this relatively short. First, I'm going to do a means test. I'm going to do it by hand, and then I'm going to do it using technology. So let me find a means example in the textbook. Okay, so number 22 on page 384. And it says, a company claims that the mean battery life of their MP3 player is at least 30 hours. All right. So in writing the null and alternative, I write the claim symbolically. It was a mean, so it's going to involve mu, is at least. Okay, now you got to think about what that phrase means, just like you did back in chapter 5. So it's at least 30 hours. Okay, so the number is going to be 30. At least, think about it like money. I would give you at least $30. Well, the smallest amount I can give you is $30, but I might give you more than that. So I'm going to claim that symbolically that is mean greater than or equal to 30. Okay, on the low side it's 30, or it could be a value higher than that. Okay, if that's not true, and I'll call that the if false, then what must be true? Well, to fill out the rest of the number line, I need everything below 30, so mean less than 30. And notice again that if you graph these on a number line, that would be the whole number line. So the null hypothesis is the statement that has equal in it, and I'm going to tell you that's got to be the claim here. So the null is mean greater than or equal to 30. That leaves the if false statement to become the alternative hypothesis, so mean less than 30. You look at the direction of the alternative hypothesis to tell what type of test it is, and so this is a left-tailed test. Because it's a mean, I know I'm going to use a t-distribution. The other thing I need to know is what significance level and what the data said. So the problem continues to say, you suspect that this claim is incorrect, and find a random sample of 18 MP3 players that have a mean battery life of 28.5 and a standard deviation of 1.7 hours. Okay, so here's the sample. This is the data from the sample. N equals 18, because there were 18 players. X bar equals 28.5, because those 18 players had a mean battery life of 28.5, and S equals 1.7, because they had a standard deviation of 1.7 hours. Is there enough evidence to reject the claim at an alpha level of 0.01? So they're telling me my significance level is 0.01. Okay. Now, again, you might be asked for the value of the test statistic. I'm going to end up using the p-value method for most of these tests, but I am, in this particular case, going to do it with the traditional method. So let me draw what I'm thinking. I've got a bell-shaped curve, my alpha over here, this area is 0.01, and I need to know what that critical value number is. Well, it's a t-distribution, so I need to go to table 5. There were 18 MP3 players, which means my degrees of freedom is 17. It's a one-tailed test with 0.01 alpha, so that's this column, 17. Okay, here's my critical value, 2.567. Now, notice that all the values on the table 5 are positive numbers. But when the tail is on the left, that actually has to have a negative value. And it sort of tells you that over here in these pictures, okay, that anything to the left of the center is going to have a negative value, but they only give you the positive one. So that's my critical value, negative 2.567. And my area of criticality is everything to the left here. Now, all I need to know is what is the test statistic. So my test statistic is X bar minus mu divided by S divided by the square root of N. Okay, so X bar was my 28.5. Mu was the value of the mean mentioned in the null hypothesis. Then S is 1.7 divided by the square root of 18. Okay, so let me do that on my calculator. All right, 28.5 minus 30. So that's the numerator. 1.7 divided by the square root of 18. That's the denominator. So then I take negative 1.5 and divide by. Now my choice here is to either copy down that number or use a little trick to retrieve the most recent answer by hitting the second key. And then this negative bar down here, see the word or the letters ANS on the top? That means it retrieves the most recent answer, which was this one right here. That's what I want to divide by. And so here is my test statistic, negative 3.74350, whatever. But I'm going to just, because my critical value had 3 decimal places, I'm going to go ahead and give this one 3 decimal places. Okay. And that value is down here to the left of my critical value. And that means I reject the null hypothesis. Okay, and remember what it was. I'm rejecting that the mean is greater than or equal to 30 hours. Okay? Notice also that the claim became the null hypothesis because now I can write my decision. Okay? The claim became the null hypothesis and I rejected the null hypothesis. So I do want this part of that little table. Okay, so my decision was to reject the null hypothesis. My conclusion, whoops, sorry, I hit. Okay, I hit my keyboard. Okay, so there is enough evidence to reject the claim that the battery life is at least 30 hours. Again, I caution you about how you write this. You have to restate the claim in words. If you wrote, there is enough evidence to reject the claim that mu greater than or equal to 30, I would count that almost completely wrong. It has to be restated in words. Now, you can paraphrase the original claim as I have done here, okay? Because I didn't include words like of their MP3 players, etc. But you may not put it in symbolically or leave it out altogether. Okay, now it's going to be very tempting to shortcut right there. But I beg you not to do it because you have the little table to use. This should be easy to do. Okay, if time consuming. All right, so let's do that same thing using the calculator. All right? Because I've noticed there's several of you that like using the calculator. And incidentally, there's a handout about this in the course content. Okay, but I'm just going to show it to you. So I'm going to go to Stat, and I'm going to go over to Tests. And I want a t-test, which is the second one down, and then I hit Enter. And I'm doing it with statistics because that's what I've got. Okay, so I go down. The mean sub 0 means the number of the claimed mean in the null hypothesis. Well, that was 30. Then X bar was 28.5. Then S is the standard deviation, that's 1.7. Then N was 18 because they did 18 players. And now here's where you must identify the direction of the alternative hypothesis. And if you skip this or do it wrong, you're going to get bogus answers. So look back at what the alternative hypothesis was. It had a less than symbol in it. Okay, so I need to go down and then over to the one that has less than in it, and then hit enter to lock it in, and then go down and calculate. This is what the calculator gives you for your answers. The first one, you notice, is the value of the test statistic. Okay? The second one is the p-value, but the thing about a calculator is that it often gives you the p-value as a scientific notation number. So let me say that if you don't already know how to do this, this is a good thing to learn. And I'm not going to write down the whole number. I'm just going to write 0.088. Okay. E to the negative 4. This thing tells you the thing that the 10 is raised to. So if I write this out in scientific notation, in the way you usually see it, it's 8.088 times 10 raised to the negative 4. Now, in statistics, almost all of these are actually negative, okay? So the value that this is raised to as a negative number means you have to go backwards 4 decimal places to the left. And where you went 1, 2, 3, 4, you fill in the blank ones with zeros. So notice there's 3 zeros, one less than this number. So the actual p-value here is 0.0008. Normally we have that as a 4-digit number. Okay? So that's the p-value. Now, when you do it on the calculator like that, you don't really have to look up the critical value. You just compare the p-value with the alpha value. The alpha value here was 0.01. The p-value is 0.0008. This number is much smaller than this number. Now, if you have trouble comparing decimal numbers, then what I suggest you do is add enough zeros at the end of the shorter one to make it the same length as the other one. So this was 4 decimal places. I've made this one now 4 decimal places. And just ignoring where the decimal is, read this as just a number, 8. Read this as just a number, 100. 8 is less than 100. That is a smaller number. And when the p-value is less than the alpha value, again, my decision is to reject the null hypothesis, and that will cause me to write the same conclusion statement. Okay, so now I'm going to change the screen. I'm going to do the exact same problem using StatCrunch. Uh-oh. For some reason, I lost StatCrunch here. So I'm going to have to pull it up. I guess when I hit my keyboard, I lost that. So again, there is a handout in the course content for how to do this. And in fact, I can show it to you in a second. But you go to, you open a stat editor, then you go to stats, and then this was a means t-test. Okay, again, if you're doing a means test, we're doing only t-tests with 1 sample, and here it was with a summary. So now I need to fill in the sample's mean. I need to fill in the sample standard deviation. I need to fill in the sample size. I need to change this to read 30. So this says mean equals 30. Now, our actual null hypothesis said mean less than. in StatCrunch, they only emphasize the equal to part, okay? The alternative was less than. And so when I compute this, you'll see there's my p-value. That's exactly what the calculator gave me. There's the test statistic, which again, that's what we found on the calculator and even by hand. And so again, all I have to do is compare the p-value with the alpha value, and I would find that I reject the null hypothesis, just like I did in the previous problem, or the previous way. So regardless of which one of these things you use, it is very simple to do using the technology. And that's really what I expect you to do. So the last thing I want to do here is to do one with a proportion. And I'm not going to do it by hand. I'm just going to go ahead and use the calculator and StatDisk, because I presume that's what most of you guys will actually end up doing in any case. Okay, so this is number 7 on page 391. It says, a medical researcher says that less than 80% of U.S. adults think that healthy children should be required to be vaccinated. In a random sample of, okay, well, let me just stop there. The claim by the researcher is less than 80% of adults think their children should be vaccinated if they're healthy. So the claim is, and this is a proportions test, so the symbol is P, less than 80%, 0.80, okay? And then if that's not true, then the proportion must be either greater than or actually equal to 80%. Okay? So the null hypothesis is the one that contains equal, so that's the if false statement. And the claim becomes the alternative hypothesis. But this is also a left-tailed test. So let's read what else it said. In a random sample of 200 adults, so N equals 200, 82% think that healthy children should be required to be vaccinated. So P hat was 0.82. At the 0.05 significance level, is there enough evidence to support the researcher's claim? So alpha equals 0.05. Okay. Now, let's do this one using the calculator, and you'll see right away what the issue, the short, easily solved issue is. Okay. So I hit stat, I go over to tests, but this time I need a prop Z test because it's a proportion problem, and we need a Z distribution. So that's at position 5. Hit enter. And notice, whoops, I must have done that wrong somehow. Oh, I guess I hit the wrong one. Okay, 5. There we go. All right, notice that I can put in the proportion in the claim because it's 0.80. But the next thing it asked me for is X, which is how many in the survey gave a specific response that I'm interested in. And I don't really have that number. I have P hat. So now I need to recognize that P hat is equal to X over N. And when I change that algebraically, I get X is equal to P hat times N. So to get the X value, I need to take P hat, which was 0.82, and multiply by the size of the sample, which was 200. When I do that, hope I don't screw this up because I'm going to do it by hand over here. I get 164. And X must be a whole number, okay? So if you get a non-whole number when you do this, you have to round it to the nearest whole number. Okay. So X was 164, indicating that 164 people out of the 200 gave the response that they thought that all healthy children should be vaccinated. Okay, the N was 200. And then this thing, again, must reflect the alternative hypothesis. The alternative hypothesis is less than. So it's already actually on less than. I don't need to change it. And then I go down to calculate. And this is what I get. My test statistic, right, which is a Z, is equal to 0.7071. But we're not going to use that as our comparator. We're going to use the p-value, right? And our p-value is 0.7603. Again, I made that into 4 decimal places. Okay. So then what we have is we compare the p-value to the alpha value. Alpha was 0.05. P was 0.7603. Obviously, the p-value is a lot greater than the alpha value. Therefore, we fail to reject the null hypothesis. Okay? And we failed to reject, so here we want to write the conclusion. The claim became the alternative hypothesis here. See, claim became the alternative. Okay, and we failed to reject. Therefore, we write, there is not evidence to support the claim. There is not enough evidence to support the claim that less than 80% of U.S. adults think healthy children should be vaccinated. Okay, so that's doing it using the calculator. Let's do the same thing using StatCrunch. All right, so let me do a new share. I'm going to share the screen. Okay, so since this is a proportion hypothesis test, we go to stat and we go down to proportion stats, one sample with a summary. So the number of successes is my N, that's, my X, that's 164 out of total observations of 200. Then my P from the null hypothesis is 0.80. And this has to be matched to the alternative direction, which is less than. And now I compute. And again, you see that that's the same p-value basically that I got doing it on the calculator. There's my test, z-test statistic. And again, all I have to do is make a comparison between the p-value and the alpha value, make my decision, and then I can write my conclusion. Guys, there's really only one way to learn to do this, and that's to do a bunch of them. I really hope that a lot of you are doing the additional homework in my stat lab. Not only is it going to be worth credit at the end if you do all of those problems, but it's just really good practice at doing this thing. So you have a lab assignment coming up soon, but I really, really, really suggest that at the very least you do some of the problems in each of the sections of the textbook just for practice before you get to that lab. Because if you don't, that lab's going to take you a long time to do, and you won't really understand what you're doing. You need to have time to go through this process several times so you kind of synthesize what it means. Okay, so we're done here.